Okay, 1 second. Okay. Did you see the recording button? It's showing start recording. Recording has start. I believe.
Yes, Mr.
Okay.
Yeah.
Okay.
Yes, I got a message. Yeah.
Yes. Okay. So I like to welcome our attendees for our last webinar for this year. My name is Mazen Hilali. I'm a senior petrophysicist with Lukoil in South Iraq. Our lecture for today will be about using IP software to interpret cement logging data. Okay, but also there will be some overview about IP capabilities there by Mr. Rose. He's the product owner, product manager or owner from Geoactive. If Dr. Muhammad want to say a few words for our attendees today.
Yes, Mr. Mazen. Ladies and gentlemen, distinguished attendees, this is Mohammed Jawad Zainul Abidin, Vice President of Technology at SPWLA Iraq Chapter. I am a senior faculty member at the University of Kirkuk College of Engineering, Petroleum Engineering Department. The Society of Petrophysicists and Well Log Analysts, SPWLA Iraq Chapter, would like to welcome you to the last webinar for 2023 about cement evaluation by interactive petrophysics IP software by Geoactive Limited Company. This webinar will be presented by Mr. Rose Brackenridge. Welcome again to Mr. Rose Brackenridge. We wish all of you a pleasant time with the webinar. Mr. Mazen, mic with you. Thank you.
Yes, thank you. Just I will have a few slides, one or two slides. Okay, let's see. Otherwise, I face problem when I want to share. Okay, let's see. Yeah, so this is our last and 7th webinar of 2023. The theme was focus on integrity. I believe my screen is shared already, Dr. Mohammed?
Yes, yes, it's okay.
Okay. This year we managed to host like 7 webinars. Okay, focused totally on downhole or subsurface integrity using tools. Okay, and the software that used to interpret the data of this tool. We like to thank all the people that help us to achieve this year successfully and close it. There we have some of our attendees and members have been attend more than 6 webinars. We will send them a special certificate, a super learner certificate, as we promise. Okay, during these days. And if anybody have any question or recommendation, he can tell us during this webinar or write us on our email. Okay, and by the way, we have faced few technical issue with our email, but you can write to us. We'll fix it. Okay, thank you all, and we'll leave the mic to Mr. Ross.
Okay. Just timing, Mazin. So we've got it was an hour session in total.
Yes, hour. Yeah. If you want to take more, some lectures take more than 1 hour. Okay, it's fine.
No, that should be fine.
Yes, and I really appreciate to introduce yourself. Yes, because we don't have your full CV. Okay, thank you so much.
Okay, let me just share my screen. Okay. Yes, welcome to the latest of the webinars for the Iraq SPWLA chapter. I'd like to thank the chapter for inviting me along, and congratulations for starting the new chapter and putting on such a good series of interesting webinars. My name is Ross Brackenridge. I'm the product manager for IP Cased-Hole. So that's IP is the software package, and Cased-Hole is the area of that product that I manage. So my previous experience, I actually studied, that was actually computer science that I studied. I then went to work for Baker Hughes for many years as a data analyst, petrophysicist. Over that time, I specialized in the cased-hole area of data analysis, so production logging, casing inspection, cement evaluation, pulse neutron. So I did that for many years, and I moved into become the business development manager for cased-hole services in Europe and Africa for Baker Hughes. I then moved to a company called, well, it was actually called Synergy at the time. We're now called Geoactive, where I took up this role as the cased-hole product manager. I'll tell you a little bit more about the company in a second. So this is the agenda. I was just going to introduce the company and the software. We'll do a little bit of background on cement evaluation. I was then going to run through a sort of standard or basic evaluation workflow. So I'll do a real life demo of that. Rather than have questions all the way through or waiting right till the end, I thought maybe we could have questions twice. So maybe after I've gone through the basic evaluation, we could have some questions on that, make sure everyone is understanding that before we go on to the advanced. Does that sound okay? Yeah.
Yes, agree. If anybody have a question, it's can write in the chat box, or we can maybe Mr. Rose tell us when he like to get the question. Okay.
Yeah. So I'll try and do more than one pause for questions, but yeah.
Yeah, that would be great.
Okay. You might have seen some similar workflows for cement in some of the previous presentations, which I was wanting to kind of focus on more sort of the advanced evaluation as well. So, okay, so who are Geoactive? To be honest, you probably haven't heard of Geoactive because it's actually quite a new name for a company. But the product, particularly interactive petrophysics, that we manage is a product that's been around for 25 years. It is one of the most established and well-used petrophysics packages globally. I think it would be in the top 3 packages that are used by oil and gas operators around the globe. It was actually created by a company called PGL, who then were bought by a company called Synergy. This is when I joined the company. Then for a period, we were owned by Lloyd's Register. And more recently, we have kind of broken away to be more of a sort of independent software company again. So quite a lot of changes in the name, but it's actually the same group of people that have been, it's the same products, same people. It's just a new chapter in our journey. So that means that we have actually had a lot of consistency in our company, the same people, the same developers, same experts. I've been with them 12 years now, but some of the other guys have been around worked together for 20 years. My manager, Derek Crombie, he was with the company when the very first line of code was written for this product. So we've had a good experience within the company and good consistency throughout. Ultimately, we do have investors and owners. We're part of these groups, but ultimately we're owned by Constellation Software. Again, it's probably not a name it's not a household name, but if you actually look up Constellation, they're one of the largest technology software companies in the world. And they buy they've got hundreds, if not thousands, of small software companies that they acquire, but they like these companies to be working independently. They feel that that's the way technology companies work best, when they don't have the overheads of a large company. And we totally agree with that, and we're very happy with the way we're working within Geoactive. So, interactive petrophysics is a very wide-ranging package. Although it's called petrophysics, it's probably a bit wider than that now. I would probably describe it as a subsurface data interpretation package. It started its life as focusing on open hole petrophysics, so calculating porosity, water saturation, clay volume. That's what it made its name for, and it's very good at doing that. And then it started expanding into, handling lots of different data types. And then we've moved in. One of the reasons I joined the company was when they were expanding into areas like cased hole, and there's other areas like geomechanics, geophysics, geology that the product has spread into. So now it really is a product that can be used throughout the asset life cycle, right from exploration, right through into production, and right up to abandonment. It can be used. And we feel there's a lot of benefits in doing that, instead of having separate software packages for doing every type of interpretation. Having everything in one place can really give you some insights into your wells that you maybe wouldn't have seen if you were looking at one data set in isolation. So in terms of that, as I said, there's lots of different areas of IP. The area that I manage is the cased hole analysis area. So this is just a list of the things that we have in IP. So we have a well diagrams manager, so we can design well diagrams and display them in various ways. We have pulse neutron modules, so we can interpret behind casing fluid saturations. So we have, and we can handle different tool types and different logging modes. So we've got Sigma analysis, and we've got more recently we've got carbon oxygen analysis module, that's part of what you can see here. And this has actually been upgraded just recently to handle like gas saturation analysis behind casing as well. We have production logging. That's what you can see here in the background in this picture, in the cross sections of flow and hold up and fluid velocity here. So that's the production logging module. It can handle conventional PL tools, which by that I mean sort of centralized tools, and also the more advanced tools such as maps and FSI tools. Cement evaluation. This is one of our most established modules. When I first joined the company, we decided cement evaluation was an area that really hadn't had as much focus as it should have had. After Macondo incident, we started seeing a lot more interest in these logs. And so we decided to build a module that could handle all the different tool types from all the different service companies and try and get some clear conclusions on that data. So that's what we're going to talk about today. So we'll come back to that. And we also have casing inspection. So that's processing multi-finger caliper data or ultrasonic tools to determine the condition of the tubing or casing. So before I talk about the software itself, just a little bit of a refresher. I know a lot of you will be very familiar with this already, but for those of you that maybe aren't in this area, just a bit of a very basic overview. So downhole cement, why do we use it? Well, it provides structural support to the well, holds the casing or liner in place. It can also prevent some, corrosion happening to the pipe by having cement there instead of fluids. But most importantly, it's really there to provide barriers. Now we put the cement into this annular space, which is behind the casing and the formation wall. We do this in a few different stages for the different casing and liner sizes. And what we're trying to do is we're trying to create a barrier that stops fluids traveling in that space. And that means when we perforate a target zone, we produce that target fluids and not fluids from above or below. And then just as important, we're providing a barrier between the reservoir and the surface. For obvious safety reasons, we don't want fluids to be traveling up through, which could cause all sorts of health and safety problems at surface. So we're trying to create barriers between the zones and between the reservoir and surface. And to achieve this, the cement needs to be strong and it needs to be distributed in an effective way. How do we know if this is the case? Well, we run CBL tools or bond logging tools to investigate the quality of that cement. What we then need to do is take that data from those tools that the service companies provide, and we need to make an interpretation on that data. So we want that data to tell us how good the quality of the cement is downhole. This type of interpretation usually happens in two stages of the well. Probably when the well is brand new, when it's just been cemented, maybe 24 hours after cementing, we'll go in and log the well. The other time that it will perhaps happen is at abandonment. So actually, once this tubing has maybe been removed out, we want to check what the condition of the cement is at the end of the well's life, just before we can plan cement barriers in the inside of the casing. So just pumping cement down there isn't always enough. So we need to check that it's a satisfactory, or people talk about good cement. What does good cement mean? So it's a variety of things. Good cement needs to have good bond between the outside of the casing and the formation, this space here. Sorry, the outside of the casing and the cement, and then the outside of the cement and the formation wall. So there's two surfaces there that we need to have a good bond at. We want to have good vertical consistency up and down the well. And we also want to have good circumferential coverage around the outside of the casing. We want the cement to be present all the way around. What we don't want to see is maybe that there's no cement at all over certain zones that we wanted to have, to provide barriers between producing zones. We might have areas that have partially cemented, particularly if we're maybe in a slightly deviated well, we might see cement settling on the low side, but then we have fluids or a gap in the high side that would allow fluids to travel through. Sometimes we can have generally very good cemented zones, but you can have pockets in that cement. Pockets themselves isolated are maybe not too much of a problem, But when you have pockets joining up, we would call that a channel, and that gives a route for fluids to travel through. So we don't want to see that either. And we need to identify if we think that's happening. So if somebody hands us some CBL data, says, tell us about the cement, what do we need to do? We need to look at, now this is for every depth level, we need to check, is the data good quality? Is there good bonding between the casing to the cement? Is there good bonding between the cement to the formation? Is there good circumferential coverage? Is there good vertical consistency? Is there any channeling or connected pockets? So it's only if we got approval on all these criteria, if you like, that we could say that particular depth is likely to provide, or has a good chance of providing a barrier or hydraulic seal in that formation. Just a bit of a health warning, of course, cement bond logs are not a direct measurement of cement quality. They're a measurement that infers the quality of the cement. So we're not absolutely proving that the cement is good, but this is the best. They're the best chance of us being able to do so. You know, short of actually perforating holes in the casing and then doing actual physical pressure tests to see if there's communication between wells, which doing that introduces all sorts of new well integrity problems. So this is the best chance of us being able to identify the quality of the cement downhole. So if we weren't using software for this, and this is where the inspiration for this module really came from, about 15 years ago or something, I was working in Kazakhstan on a project that was doing numerous cement bond logs on a field there. And the data used to be sent in to me, and I had to tell them the quality of the cement as quick as possible, because the rig was actually waiting for a decision on it as well. So I actually found that the best way to do this, I used to print out these logs. I used to get the field print. I used to print them out, and I would put them along the corridor in the office, and I would get a marker pen, and I would go right through all the log, marking on where I thought was good bond, poor bond, where the formation arrivals were coming through. And then I would look at the value of the log. I would take the log interpretation chart for that tool. I would go, okay, casing size here, attenuation. Okay, at that depth, I've probably got 100 PSI cement. Then I would type up a spreadsheet, and it was, to be honest, it was a painful process, and it could take hours because the logs were quite big. It's quite easy to make some mistakes in reading these charts, typing in values into a spreadsheet, sometimes at 3 o'clock in the morning. Used to always seem to happen at 3 o'clock in the morning. So that was kind of then, especially, there's got to be a more efficient way of doing this. And that was when I moved to the company that's Geoactive now, we designed a software module that could take data from all the different service company tools, and very quickly it would step you through in an intuitive workflow to take you from raw data to a clear conclusion on the condition of the cement. And that was another problem with CBL logs up until that time. They were very subjective. If you took a log and put it down on a table with 5 people around it, each person might have a different interpretation of, I think, oh, it looks pour cement through there, and somebody else might say, oh, well, that's because that because of the borehole fluids, and it's probably okay. So there was a lot of subjectivity in the interpretation. So this is trying to get from raw data to clear conclusion as quickly as possible. So when designing the module, I said we need to handle all different logging tools from all different. This is just some of the companies out there that you might receive raw data from, and they've all got their own names of tools. RBTs, SBTs, URS. Now, for someone in an operator position who might be dealing with various service companies, and each service company may be having 2 or 3 different tool types, that can be very confusing. And our software is designed to help those people. So we want to make it, we want to kind of try and simplify the confusion around that. So what we did was, if you actually look at, don't look at the names and the sort of marketing of these tools. If you actually look at the hardware of what they do, we believe that you can put them into categories. We have traditional CBL tools, which worked with, you were really looking at one amplitude curve. Now, these days, nobody really, it's very rare that these tools would be run these days, but you might come across some historical data. And then we moved into having more radial measurements. Pardon me. Radial measurements, which have more than one sensor. They're looking at the condition or the amplitude around the casing. The SBT tool from Baker Hughes is kind of its own category because it's a bit like these tools, but it's only one that has physical pads that is actually touching the casing wall. And then you have ultrasonic tools. So these are the high frequency, high resolution acoustic tools that are spinning around and measuring the impedance of the cement. Now, Schlumberger, probably the best known one is the USIT from Schlumberger, but you have URS from Weatherford, CAST from Halliburton. There's now the Ultex from Baker Hughes. The service companies won't like me saying this, and I know there is some benefits of some of them over the others, but for the end user of the data, they're quite similar in what they record. And then more recently, when we moved into different types of cement, there's a new generation of tools have started being developed. The most, probably the best known one of those is Schlumberger's Isolation Scanner, and more recently Baker Hughes Integrity Explorer. So I think when you're dealing with data and interpretation of these data sets, I would always think to yourself, well, what category of tool am I looking at here? And it just makes it a bit simpler to understand all these different tools that are out there. So if I was doing interpretation on a software interpretation on one of those more standard tool types, this is what I'd be doing: setting up the tool type and getting the data defined. I would then define my well diagram. I then need to pick collars, because every one of these tool types, they're all basically acoustic measurements. So every time you go past a collar, you get a spike. They're all the same. So you need to identify where those collars are so you can remove that data from the interpretation. We then build cement maps from the raw data. We look at the coverage of the data. We then look at the raw waveforms to determine whether we can see formation arrivals. And then we bring all that together to draw some clear conclusions. And we have this traffic light grading that we give to each zone. So that's the workflow. So I'm actually going to open up the software and just show you that workflow. So hopefully you can still see my screen now. We're looking at the software.
Yes.
So this is interactive petrophysics, and you can see down here, down the menus, we have, if we go to interpretation, this is like all the open hole interpretation. This is what IP is best known for, the workflow of clay volume, prostate water saturation, cutoff and summation, NMR in there as well. And then it has more sort of advanced things, mineral solvers, saturation height modeling, formation testing. And then we have these other sort of specialized areas. So we've got machine learning with neural networks, cluster analysis, and there's a few modules in there that are exclusive to IP as well. Domain transfer analysis is a sort of premium curve prediction module. Experienced eye, which helps you decide on which one of these methods is the best one to use for your data set. What else do we have? Geoengineering. Here's a mix of rock physics, geomechanics. We've got a whole workflow for geomechanics, including pore pressure, acoustic waveform processing, geosteering. Then we've got a whole section on the image log interpretation for geologists out there. Of course, everything can be done multi-well. We also have the ability, the user can actually create their own applications as well in here. But the area we're looking at today is encased hole. Here's my cased hole modules, and it's this module here, cement evaluation. So this example I'm going to use is a Baker Hughes SBT. And that's the pad device. So it's got 6 different pads, each giving attenuation measurements, and a 5-foot waveform, gamma ray, a few other curves here. So that's all I've got. All I've done is taken in some raw data as I would receive it from the field. And then I'll just go in and open up the cement evaluation module. So first thing I do is select a tool type. You can see all the different tool types here. It's SBT. Now I'm not going to go through every click and every parameter here because we wouldn't have time, and it's not meant to be a training course as such. So I'm just going to kind of show you how quickly I can kind of skip through the workflow. So I've defined the tool, and then say, okay, I'm going to bring in all my raw data from this data set. I'm going to go out to a data set called results. I want to rotation correct the data. I've got 6 of the attenuation curves coming in for as my bond sensors. I can then QC the data. So there's the data. This is a bit like what the field print would look like, or the field, I shouldn't say print anymore. I don't really get hard copies, but the field display, field log. So this is just showing you the main curves. This is just a way of checking that you're happy with what's being taken in. Each tool type has different things that you would check. In this case, we have this delta T min and max. If these two are too spread apart, that means that there could be problems with the tool position. But that looks quite nice data. The waveform looks good as well, so I'm happy with that. So now I need to tell the module about the completion information. So I could type all that in here if I wanted, but in IP we also have the well diagram manager. So if I already have a diagram created, I can bring that diagram in. So there's all my casing sizes. Cement that I've got here, this is a very simple case that I've got conventional cement with a strength of 2500 psi. Now if I just apply that, there we go, we've got our diagram. The other thing that's done is, remember I was saying that there was those log interpretation charts for the different tools. All those charts have been digitized in the background. So what it's doing is it's saying, okay, my logged interval is down here, which is 7-inch casing. I've got 2500 psi cement, or I'm supposed to have 2500 psi cement. That's gone and looked up the chart, and it's worked out that to have 2500 psi strength cement, we're looking for a log value of about 11. So that's interpreting the cement strength to what the log would actually be showing you. So now we know what to expect for this cement and this casing. As I say, we need to identify all the collars, so we can do this mostly automatically. We at least first try and do it automatically by just putting some thresholds in here. So this is the CCL data, and this is my interactive parameter. That's why we're called interactive petrophysics, because we have a lot of these interactive parameters. Instead of typing in a value, we like to interactively choose it. So if it was too high, I would miss some of my collars. If I get too low, I pick up noise. So I'm just looking for that point where it looks like we've got most of the collars there. If there's something I don't like, I can zoom in, say, okay, that's the collar, this isn't the collar, so I'm going to delete that one. Now I'm looking, I can see every 35 feet or so, I'm getting a collar, so that makes sense, and there's my collar list there. So I'm happy with that. Now on to the bond map. So this is where we create, oh, I needed to run the module at this point. So if I run that first and then launch this plot. So this is us taking raw data and building our own cement map. So you can see if I adjust these cutoffs here, you can see the cement map is changing as I do that. So this is probably the most important part of the workflow for the analyst, because they need to know where to set the cutoffs. This dashed line is telling us where 2500 psi cement would be. This red line is telling us where free pipe should be. So we can see we've got free pipe at the top. We've actually got more than 2500 psi strength in some areas. So what I tend to do is we've got two levels of cutoff. This green one, everything above that will become green, and that's us saying that the cement has good strength, as good strength as we would have expected based on the parameters we were given about the cement. So everything above that is 2500 psi is green. But we don't need it'd be nice to have 2500 psi everywhere, but we don't really need that much. How much do we need? Probably 500 psi would be strong enough. So this other parameter, this orange one, is what we call the acceptable parameter. So it's almost like how low are you willing to put that cement strength to. So I could choose something interactively here, but I might want to have an exact number that I've agreed with everyone. Let's say we want our good strength to be 2500 as we expected, and let's say 500 psi is the lowest strength that we would accept, and that's updated these cutoffs. So this is our orange will represent 500 psi or more. So then we're adding up the circumference of the good cement and the acceptable cement, and that's what you're seeing here. 0 to 100%. That's the percentage around the borehole. And then we set a cutoff that's saying how much coverage do we need before we would say this depth is good enough. So I've set this to about 85%, 85 or 90% usually. But you can see as I move that, I would get more or less. This represents a pass. So the higher I put that, the less passes we have. So what we're taking from this whole screen is really this flag here that's saying whether we've passed or not. And this is passing just between the casing and the cement. It's also an opportunity to flag channels. If I saw some channels, this tool type's probably not the best for seeing channels because it's quite a low resolution anyway. But let's say there was a channel that, you know, we're still getting some pass marks through here, but we said, I'm really not comfortable with this area. So I could say, I'm going to veto this area. Whether it passed or not, I'm going to veto it because I think there could be some channeling through here. You might want to mark on a few areas here. So then you have past intervals and then intervals that you've effectively vetoed because you think that there's potentially channeling. Okay, we're moving along. Now we go on to formation, which is where we take the VDL. This is the VDL that's going from the receiver, the transmitters to the 5-foot receiver. That's a longer space, so it's seeing more of the formation. The only way we could be seeing formation arrivals on this is if there's connection. In this case, must be cement that's connecting the casing through to the formation. So I'm looking for formation arrivals that would look something like the same pattern as like the gamma ray, because it's going to follow lithology. So you'd probably take a bit of time on this and go through and see where we can see formation arrivals that are following the gamma ray there. See that? So I could mark on that so that I'm happy with those formation arrivals there. I don't really see those at the top. It's more like straight lines. I heard somebody saying about cement bond interpretation, you can summarize it in one sentence saying straight lines are bad, wiggly lines are good. And that's a pretty good summary of cement evaluation. So you would take a bit of time going through looking for arrivals there to speed up this process. I'm pretty much going to say that there's good formation arrivals right through this bottom section. Okay, so there's my formation arrivals. Now I'm going to bring everything together. So everything we've done so far, and we get this list. Is it bonded? That was where we used our cement map to decide if it's bonded or not. Was there channeling or not? And is there formation arrivals or not? And we get this grading traffic light system that says if it's failing everything, we get the red light. If it's passing some, we get amber. If it's passing them all, we get green. So we're wanting to see a lot of green on here. So it's quite a big list. We're really interested in probably, it's the good zones that we want to find out. Where have we got good zones? So we can deselect all the amber and red just to leave the good zones. But look here, we've got a zone here that's 8 centimeters in height. That's not going to provide much of a barrier. So we can put a minimum vertical height in here as well. For this type size of casing, maybe like 10 feet, or we're in meters here. So I could put in 3 meters would probably be a good value. And here I have all the zones that have good cement that have greater than 3 meters continuous good cement. So we can look at this on the log plot as well. Here's the different stages we went through: the well diagram, collar picking, cutoffs, building our cement map, then our coverage, checked for channels, checked for formation arrivals, and then we have our final traffic light down the side here. Okay, so that's great, but I've got someone at the well site that's waiting for me to give the results. So what we can do is go to a report, generate an automated report. So here's my first page. Second page is all the casing details, the options that I used, the parameters that I used, and an explanation of those parameters. And we have some statistics. So that's saying that we have 86 meters of very good, continuously good cement. If you put on the 3 meter minimum vertical, that reduces to 66 meters. And you can see how much has failed. This is our filtered table where all the good stuff was, the depths, and then there'll be a few pages. That's a full table that shows you the condition of every zone. And that can be output to Excel file, a PDF, or a Word document, and can be sent off to the well site or whoever's making those decisions. So that's pretty much the workflow of the module on quite a sort of standard tool type. Is there any before I go any further? Is there any questions on that that workflow at all of the steps that we took through there? No.
I have a question myself, but we'll keep it to the end.
Okay.
No problem.
Yeah, I'm just looking at the time, so I better hurry up a bit.
So
Okay.
let's keep everything to the end. Okay.
Yeah. Okay. So that was just the sort of traditional workflow. So let's go back to the slides here. So what happens when we introduce advanced cements? You know, might call these lightweight cements or foam cements. I've given them the term advanced to sort of cover all those. What are they for? Well, at one time we only really used conventional G-class cements, and all of the sort of tool technology was based around those. But then when we started dealing with more sort of high temperature, high pressure wells, there was a need for more flexible cements, as the completion or even the reservoir might kind of expand or retract with pressure and temperature. So we need more flexible cement. Having lightweight cement can also avoid, if you've got quite weak formations, you don't want to sort of introduce fractures or into the. There's hundreds of different types, different combinations out there, but this is just a few examples of. I mean, you can have just lighter weight cement that has a much lower density than conventional cement. You can have cement with actually things inside, like ceramic or glass particles or beads in that cement, which lowers its density as well. And you can have like foam-based cements that have nitrogen gas in it that can make it even lighter. Now that causes problems. When they invented these cements, no one thought about the poor data analyst that was going to have to deal with it, because what you find then this is like acoustic impedance that would come from a USIT or another one of those tools. You have these values when you've got conventional cements, but when you get into lightweight cements, the impedance value starts to look very similar to, there's oil-based mud in particular, and even water-based mud. The change between the fluid and the cement becomes very slow. And you've got to remember that these tools only have an accuracy of half a unit. So that becomes problematic. So what can we do about this? It's not just the ultrasonic tools, all the amplitudes and attenuation tools have the same problem as well. So what could we do about it? I mean, we could just adjust our expectations. You know, when I said that tool was supposed to read 11 units in good cement, maybe it's only going to read 4 units. That's not very, you know, we don't know how much effect we should be reducing that expectation by. We could do a qualitative cement. We can still say this zone is the best zone, the best cement. That zone is the worst zone, that's free pipe. Everything else is something in between. Yes, we can do that. It's not very, doesn't give us much confidence about, we're not really learning about the real sort of strength of the cement. We could do a derivative analysis. I'll talk about that in a moment. Or what eventually happened was the service companies started working on new technology to deal with this. So I've got focus quickly on these 2 options here. Derivative analysis. Derivative analysis is using the same data that we already had, but it's using the basis that rather than look at the actual value, the impedance or the attenuation value, we actually look at how much it changes. Because if you have a fluid, it's very consistent. It's very, you know, what you call homogeneous in its texture. So you would see quite kind of smooth response on the tools. But solids are technically, you know, they're a bit rougher. So it's not going to be such a smooth response. So if we look at the rate of change, even if the actual value of the log has become confusing, looking at the character of the log, we can do. So this is an example. We can make a new cement map based just on the derivative value. This is the traditional way of doing it with impedance. So this isn't lightweight cement. This is showing how this 2 different methods can be used to measure the same thing. Here we have impedance, and our derivative method can kind of see the same character of where you have good cement and not so good. There's limitations in this. Only really seems to work at all in ultrasonic tools because they're probably the most sensitive. Some of the other tools have got more sort of averaged measurements between pads and things, so it doesn't work so well on those. Some foamed cement can actually be a bit like liquid in the sense that it's got a good sort of homogeneous texture. So sometimes that doesn't work. And it only tells us that there's something there. It doesn't tell us anything about the strength. It's just saying, yes, we can see a solid material in there. So to be honest, I would say this was a way that geoscience people it was a bit desperate really, because we were trying to use logging technology that wasn't really built for the cement that it was logging. So we had to be inventive of ways of trying to interpret that data. It's not an ideal way of doing it. So what we then have is advanced tools that were developed. 2 main ones in the market being Schlumberger's isolation scanner and more recently Integrity Explorer from Baker Hughes. Isolation scanner is basically the same as the USIT. So it's got the USIT ultrasonic section that measures impedance, but it also has another measurement called the flexural. So rather than the sort of direct compressional measurement that this is getting, you also get this flexural acoustic measurement that's kind of traveling up and down the casing. And by looking at the 2 of those, you can get a better indication of what is a solid material, what's a gas, and what's a liquid. So it's taking another measurement along with the traditional one and bringing a new interpretation method. Then there is Baker Hughes one. It uses pads, and it's taking measurements between the pads. So you don't have the problem of borehole fluids, but then because it's pads, there's like 6 or 8 pads that you don't have the same resolution as an ultrasonic, but and it has 2 measurements, shear wave and lamb wave. Lamb wave is basically a flexural measurement as well. But what's fine with this is that the shear wave, instead of a compressional wave, gives a much better resolution when you're looking at the difference between lightweight cements and fluids. So that kind of solved that problem. The downside was that shear is very affected by microannulus. It will just kill the measurement. So that's why they've got this lamb measurement, which is like a flexural as well. And between the two, we can make an interpretation. I'm not here to say, which tools are better than others. What I'm really looking for is sort of commonality between, so how do we interpret this data? So although there are different types of measurement, electromagnetic and ultrasonic, we basically end up with 2 measurements, a primary measurement and a secondary measurement. So we could use one or either of these for each tool type, or we could use a combination of the 2. Okay, so you'll hear me talking about primary and secondary measurements. That was just a way of me kind of standardizing what we're getting from different advanced tools. Okay, now I'm not going to step you through the whole workflow this time. You'll be happy to hear, but so I've got one that I did earlier. Go on to this one here. So this time it's a Baker Integrity Explorer. So instead of having one set of data coming in as the bond sensors, I've now got 2. So I've got shear and lamb. When we actually look at the raw data, there's actually 2 lamb measurements and 2 shear. For some reason, this data set didn't have one of the lamb data sets, but you can look at the raw data and determine the best ones to use. Usually Baker recommend using the high frequency shear and the lower frequency lamb data. Lamb is basically another word for flexural. It's just the different service companies have different. Completion's the same, collar's the same. We introduced a new way of calibrating data because these, particularly the Intex, requires some additional calibration. Some of the sensors seem to be kind of offset with each other, so we developed a way of calibrating. Then instead of creating one type of bond map, we're creating a shear measurement, which is just like we did before with SPT. Here we've got the zones that are passing here. But then we can do the whole thing again with a different measurement. This is the lamb measurement. Okay, so we've got two different ways of trying to tell the same thing. Formation arrivals is just the same as before. Choosing those. And then we bring everything together again. So here's the results. Now, what we've also introduced is different options here of how do you want to actually grade the bond from casing to cement. So all these different methods, they're basically just all trying to determine this here. Do we have good circumferential bond to the casing? So which one are we going to actually use for that? So we could use the shear, and just by clicking this on, all the results will be dependent on the shear. We could use the LAM. What I've done here is either. So that is, if I look at this, we've got one interpretation using shear. That's the pass mark for shear. And we've got the same for LAM. It's got its pass mark, and it's saying this column here is the flag that says if either of those ones have passed, I'm going to give it an overall pass. So we're basically giving it two chances to pass, the traditional measurement or the shear measurement and then the LAM measurement. That's one way of doing it. But then we can also use what we call a combined method. Now, when I use combined, if I run that and launch the plot again, you'll see that now we've got this, instead of two results, we've got this one combined result, which is like a solid liquid gas map that we've created here. And to help define that, we can use this cross plot. So what this is, I didn't, did I actually? Yeah, I did. Yeah, it's better. Okay, so so what we have here is the data cross-plotted. So we've got primary and secondary. In this case, this is shear along the bottom and LAM up this side. And what we can do is we've got this solid area here, gas, which in this case, there's no data landing in the gas, and a liquid area. And we can interactively adjust this real time. So as I do that, you'll see the map updating. So I can choose my cutoff point for that. But what the in-text also gives you is, remember I said that the shear data is terrible when it gets into a microannulus, but the LAM data not so. So we've also got this other cutoff that says, okay, it's not a solid, but it's not fluid. We believe it's a solid with a microannulus, and that's what the yellow is. So what we end up with here is we've got actually quite good coverage between what's solid and what's solid with a microannulus, and we can then use that as our final bond interpretation. And we do the same thing with the isolation scanner as well. We've got these interactive cutoffs. It's also got a way, there's actually black dots here, which is representing where my free pipe, because I actually defined a free pipe zone earlier in the workflow. So where the black, I'm actually going to change this so the black dots are on top of the green ones because you can't see them that well, but you can then use that to choose your cutoffs here. We know this is free pipe, so anything above that is probably a good point to use your cutoffs to give you a more accurate bond map. And then it's just bringing it all together in the same way. This time we have, okay, this is in feet. So we have only three intervals that have continuously good cement with 10 feet or more. So that was advanced workflow. That just shows you how we updated that a bit. Instead of one bond evaluation, you have two. We have a calibration stage and additional options. That was our different options using one of the measurements or either of the measurements or doing that combined workflow. That's just an example of the isolation scanner doing the same thing, solid liquid gas map here. Again, there was no gas in that one, but you can see we've got the quite good coverage at the bottom there, not so good at the top. Yeah, so that was presentation. Sorry, I've actually gone a bit 10 minutes over. So, but just to sort of summarize about the software, ultimately it's all about safety, isn't it? We're trying to identify poorly cemented zones to try and avoid, serious health and safety issues occurring. It saves time, using this. You wouldn't do an interpretation as quickly as I just did it there. That was just for the benefit of the demo. You take a bit more time and attention on it, but it's still very much quicker than doing any sort of manual interpretation by just eyeballing the logs. You can then actually make better decisions. You're taking something that's quite sort of high resolution and lots of data to actually something that's quite simple and easy to understand. Quite often the person making the decision at the well site, he doesn't care about attenuation of logs or impedance, or he's just saying, you're the expert, tell me where's the good cement. And this is a very good way of getting that clear conclusion. Once you have parameters that work for you, you can then keep it consistent across different wells. So you're always getting a consistent result. And then, of course, being part of IP, we can also combine this with other data that's interpretations that's been done in IP, production logs, casing inspection, open hole interpretations, porosity, saturation, all in one place. Yeah, so thank you for listening and watching. I'd be happy to take any questions if we have any.
Yeah, thank you, Ross, for this really informative lecture. Okay.
Welcome.
I really like this part about advanced log integration in the IP. So many people right now are aware IP is not just an open hole software. Okay. And totally agree with you. Okay. The goal is to transfer all these logs that have many curves, like the cast or this SPT from Baker and the advanced one from Schlumberger and Baker, to something that drilling engineer, workover engineer, perf guy on the side just see this is the good cement. Okay, the decision maker. Okay. I have two questions, but let's keep it after the attendees question. I see there is 2 questions in the chat box, or 3. Okay, if you can see the chat.
Okay, I think one was just a.
Yes.
One was just a thank you.
Mohammed Jafar is asking about fast formation in the process. Fast formation.
Average compressional. Which tool should be run to get excellent cement evaluation? So our fast arrivals, yeah, I mean, we should be able to, I mean, casing, yeah, is coming in at about 58 microseconds per foot. So yeah, it can get mixed in with that casing arrival when you've got very high low compressional delta T. Which tool? I wouldn't have said there's a particular tool that would deal with that better. It just means that we need to take a bit more care looking at the first arrivals and just seeing how on the waveform we need to be careful and expecting to see our formation arrivals further up. Obviously, it's not going to have any effect really on the casing to cement, that circumferential bond. It's really when we come to the connection of the cement to the formation that we need to be careful what we're looking at, if it is formation or casing arrivals. I don't think it's so much the speed that it comes in. It would be more the character can cause more problems. So if we have very straight carbonates, something that I would say that can cause more problems because we don't see and it's hard to tell what's. Remember, straight lines are not good for cement evaluation, and sometimes carbonates can give you a bit of a straight line, and you can't tell the difference. So, any QC or correction module for tool eccentricity or piece of iron effect correction? It's not something that we've got. I mean, I just see that the module would identify if it looks like we have problems with tool eccentricity. That the more I'd probably say that's probably an issue for the logging provider to deal with if that is occurring. It would be nice if we did have maybe a tool to recalculate some of the images from the raw and try and. We then get into kind of difficulties with all those different technologies, all the different tool types. When we start trying to almost recreate the raw data, that's when it can be quite difficult for a package that's trying to do all different tool types. So nothing specifically in there other than to identify tool eccentricity, not so much to correct it, but it's a good point. It'd be nice. Something we could maybe look at. And the question from Emil is TechLog.
I get mixed up between TechLog and IP.
So the question is about TechLog. Is that?
Yes, it is out of scope of this lecture. I don't believe we can put comments.
Yeah. So that would be a competitor software of ours. But the other thing, what I would say is obviously Schlumberger is a log provider as well. A tool provider as well as software. So there obviously will be quite a lot of focus on their own tool types, whereas Geoactive do not have logging. We're not a logging company, so we feel we're completely neutral. We treat all the service company tools with equal attention.
Yes. There's a comment from Lamris from Halliburton.
So you could combine. Yes, someone else was asking me about that recently. So usually when we have the ultrasonic, which is a much higher resolution measurement, we usually favor that over the standard sort of one curve CBL amplitude. Some people have also said, we don't really like the idea of just throwing that away. We should be able to use it in the interpretation as well. So yeah, we've been looking at ways to maybe you could zone the interpretation and say, okay, maybe my ultrasonic didn't look good in this zone, but my CBL amplitude does, so I want to pass that zone. So some way of using both measurements is something that I've been asked for in the past. So it's a good point, Lamris.
Okay. If no further question, maybe I will just have a few things. So for this, you mentioned something really interesting. You name it as experienced eye.
Oh yes. Yeah.
You said this is like you can select the module you want.
Yeah. So we have lots of different machine learning techniques, methods, like neural networks, multilinear regression, and what we've found is when anyone's using these methods, they always try the different methods out to see which one they think is the best. And then on top of that, if you have 20 input curves, which combination of those curves is the best to get use? Now, the amount of different combinations of, if you want to reduce 20 curves down to 8 curves, the amount of combinations is huge. So this module takes your data set and it works out which of the curves has the most influence on your target curve. So if you're trying to predict permeability, it would rank all your curves with how good are each of these at predicting. That way you can decide which curves to use. And then it takes those curves and it runs it through neural networks, multilinear regression, DTA, the different methods, and gives you a table that says these are this combination of curves and this method came out with the most accurate result. So it's a time-saving technique that you can, what would take days to do, really, to try all those different methods with all those different combinations. This does it up front. We did a paper on that at I think it was last year's
video on YouTube or something.
I don't know if there's a video about it. But if it's something I can find something and pass it on to you that you could spread it around.
There is you have one guy experience in machine learning focus, Andy?
Andrew McDonald, yeah. So he's my colleague.
I remember he did such thing, but I don't know if he
published it or not. Yes, I think we did. Yes, he did do a webinar on that. So yes, I could share. I could share a link to the webinar.
Because I don't believe I saw the recording for this anywhere.
Yeah,
there was a webinar. Yes.
Yes,
we really appreciate.
Yeah, you're right. There's one. So I will send the link to yourself, and you can pass it around the group if you want.
Yes, that's really great. There is a question from Mohammed Jafari. Actually, that was on my list. So we can make zonation for cement interpretation also. Like you have light cement, heavy cement, TL, and heat cement, and you want to separate the interpretation.
I'm not sharing anymore, but just very quickly. So if right at the beginning, if I said there was two different cements here, conventional and lightweight, for example, and that will then create two different zones on the interpretation. So you can see here, I've got two zones, and you can have different parameters. So there's two different zones here, and you can have different parameters per zone as well. So you can almost break it into two different interpretations that kind of get added together at the end. So I don't have to have the same parameter here as I do here. I can move that one independently. So yes, we can zone it depending on different cement types.
And in very easy way. Just like got it. Okay, nice. So let's see. I remember like before, okay, I was using IP for a while. Like when I was going to, it was LR, it was belong to
Lloyd's Register, yeah.
Yeah. When I was entering this website, there is a page. I go there and there is, I don't want to say tens, but there is too many learning video for IP. Okay. For IP, is this one still available? Like learning video on YouTube or something?
Yes, so we have a YouTube channel. So if you go to our website, geoactive.com, I'll just put that in the chat there. There's a section in there called webinars, and you can see all the different webinars that we've actually done.
On your website? Okay.
Yeah. We also have a YouTube channel. I could try and quickly put a link to that as well.
Somebody asking you for provide demo. Mohammed Jafari from, I believe, Algeria.
a demo of
software to get hands-on
Oh,
experience.
okay, yes, absolutely.
Okay.
I'm just going to pass on the link to our YouTube channel. Okay, so that's it in the chat there. So that's our YouTube and our website. So you should be able to find quite a lot of interesting things in there. And anyone, feel free to get in touch with me. I think if my email address is probably on this webinar, you can, if there's any more questions. Did I miss anything there?
No. I'm trying to.
So there's a question about uploading the. So I think you're going to upload the recording.
Yes,
is that correct?
Yes, for sure, always.
Yeah.
So let's see. Just final question from my side. When you upload this, what you call this Baker tool, the new one?
Intex. Integrity
Intex.
Explorer. Intex.
Integrity Explorer. I believe this is a new version of SPT. So there is a template when you use Limburger or Halliburton, like you just load the data, and there is a template. It will plot all these too many curves.
Yeah. So it knows once you select the tool type, it will know which curve names it's trying to look for. It will try and find them automatically. And if there's any charts involved, it'll have the digitized charts in the background. And so yeah. So the tool template takes care of a lot of that.
Okay. Let me check. I don't believe there is no more question. Okay, and this will conclude our event for today. My appreciation for these lectures. Okay, it's give us more insight regarding.
You're very welcome.
What's happening in the IP software world nowadays. Dr. Mohammed, if you're there, if you want to say something before we conclude.
Yes, Mr. Mazen. Really, it was a very important lecture today. Thank you, Mr. Rose, about this distinguished lecture. We hope to see you again in 2024.
Absolutely, yes, I hope so.
Thank you.
Yes. Thanks for all attendees of today. Okay, see you next year. We'll have most probably like a year focusing on production logging, mostly. Okay, we'll agree on that. We'll announce that later. Okay, thanks all, and see you next time.
Thank you very much for having me as a guest.
Thank you, Ross.
Thank you very much.
Much appreciated for your time and support. Our regards. Bye-bye.
Goodbye. Thank you.
Okay, bye for now.